Yes,
There's special effects on
You have to
everyone.
do 3, 2, 1. Go.
Oh, I'm doing sparkles. Oh, do you want me to do the sparkles
No,
while you
the
press
3,
it?
2, 1 is
No,
the
it's
cool
already
start.
just put your face in
Cubby!
Oh, it is?
Cubby! Cubby! They got away last
I
night.
know.
There you go.
Did you already shot for it?
Cubby! Okay.
Pretty good.
Do a
All right.
for every rod.
So yesterday we came up with this. Little e big GM over r squared. We got this v equals the square root of big GM over r. Now, here's what's important. Okay, listen to me, listen to me, listen to me. What does that mass represent?
The mass of the Earth.
Well, in this case, we're finding little g, right? So this isn't necessarily something that's going to be in orbit, but it could be. But more importantly, it's the you're finding the gravitational acceleration, right? Okay, you're finding when you drop something, this is the gravitational acceleration you experience. This is not the mass of what you drop. Okay, it is the mass of what it's falling towards. Now, notice this is r squared. So, and regardless of the r, where is the r measured from?
The center to the object.
Yes, it is always a center to center distance. It is not a surface out. Okay, it is because we treat everything as being a point mass. So, if I double the radius, so like let's say for example, here's the Earth, right? Boom, we're here. So if I make that radius bigger, let's say that I double that radius to 2r. Okay, so in other words, I'm here, it doubles to 2r, this now becomes the new size of the Earth. Same mass, but I've doubled the size of the Earth. What's that going to do to my value of g?
Multiply by
4 less.
Multiply it by 4, so g would become 4 times greater.
Yeah, the reciprocal of 4, of course.
4 times less.
4 times less. Why, Kendra?
Because it's at the bottom of the fraction and it's squared.
Yes. So you're right if I reduce the radius by a half.
Yeah, the reciprocal.
Okay, but this isn't what I do. Okay? Because look, this is why Kendra's right. Because it's GM over 2r squared. So this becomes GM, come on,
Something's wrong with your pen.
over r, I think I'm out of electrons, times
Get it? That was one of his jokes.
4, right? So it would be 1/4 as much, because it's 1/4 of that initial quantity of GM squared. So you have, because it's a squared function, you have to pay attention to that. Now, let's talk about this one. With this one, if I double the radius, just generally, what's going to happen to the velocity of the satellite? This treadway. If I make the radius bigger, what's going to happen to the velocity?
I thought you said 2 times. Well, I guess it's...
No, that was that one.
Okay.
That's the gravitational acceleration.
Okay.
I'm over to this one with the velocity. If I make the radius bigger, what's going to happen to the velocity?
Of what?
The orbiting satellite.
Oh.
Increase, decrease.
Yes, she's right.
Did you say increase or decrease? Huh?
Right? Decrease. Right?
Why? You're right. Why?
Because you're still dividing it by, like, well, it's square root.
And I'm dividing by a
You're
bigger
dividing
number.
it, yeah.
Yes. But that's the bigger answer.
Hey, she got there somehow.
You just gotta be confident.
She really did get there.
You had it.
It's
Yeah.
just a process.
You look at people in a way that makes them
Yes,
uncomfortable.
yes.
You're like, you're wrong. No
She
matter
has a
what.
I
point.
never said
That's what it
no.
feels like.
It's like it's a
Your
loop.
face
just says something completely different than what
It's honestly.
Yeah.
Like it's a
Because I
loop.
think you don't understand what we're trying to say, but we do, and you like look at us like this.
Because I
This is your
couldn't
look.
hear what she said. Somebody was over here flipping a water bottle, and all I heard was that. I was like, no. That was I can't.
Yeah.
Okay, no, stop.
No way.
That was my water bottle. Please don't take it.
just because I landed that,
That's
you have
not-
to give
You
it back.
getting landed? No, you didn't.
Can I have my water bottle?
Ground.
If you had landed that, I would have cried.
All right. So, what that means, as satellites go into higher and higher orbits, the velocity becomes smaller and smaller and smaller. Okay? Remember that? Remember that? Remember that. Now, we have one last big equation to come up with. And it still goes back to, here's a satellite orbit around the Earth. Okay? Same idea. But now I want to look at the equation that involves centripetal force that involves the time for one rotation. So what's the equation that involves centripetal motion and period? Centripetal force equals what?
mv squared divided by r. G m1 m2 divided by r squared.
No.
That's
They
F.
want to take
That's
mass and
F.
acceleration.
Divided by
Huh?
FC equals everything.
Mass times centripetal acceleration.
4 pi squared
R.
over
G squared.
Squared.
See, well, we didn't have our
Big dog.
big dog out.
Yeah.
Big dog.
We need
Dogs
that.
at the big dog.
Okay.
Ground everything.
Now, that has to equal the gravitational force, which is going to be mass 1, mass 2, we'll call this the mass of the satellite, we'll call that the mass of the Earth, and then we got big G, and then we've got all that over r squared.
Yeah, so.
So
So
again,
cancel out the R.
what's going to happen to the mass of the satellite?
If what?
On, if I,
Oh,
if
you're
I,
canceling
Really, I was
them out.
like, you're like
Cancel
really
them out.
looking at it.
yes. So you
Maybe I'll
will
just write the
notice
final
I will
equation.
never give you the mass of the satellite. I'll never tell you what color it is. Okay? I'll never say, oh, it has components made in Indiana. Not relevant. Okay?
out one R with the R's, right?
Most of it.
Why are we equaling those?
Okay? So, because I said these equal because the gravitational pull has to be creating the centripetal force. That's the whole point.
What is that first letter on your left?
Where?
That, what is that?
It's just big G.
Okay, I thought it was a GT.
No, it's just big G.
Okay.
Okay?
Yeah, you make
Now-
them so weird.
What I want to do is cross multiply. So I'm going to have big G, mass of the Earth, times t squared is going to equal 4 pi squared r cubed. Right? Now, this is what I have on your equation sheet. So this is like the Swiss Army knife of all things relating to period and radius with satellites or moons or something orbiting around a planet. So the reason I just left it like this is because once you get it here, then you can solve for anything. So let's make sure that we can all do the algebra. So, Mr. Rollins.
Oh, God. Why?
No.
Why?
I want this solved for period. I want t by itself.
Divided by G and E
And
square root.
beautiful.
Only a doctor would have got that.
So I'm going to get t by itself. So I've got 4 pi squared r cubed over big G mass of the Earth. And then I'm going to take the square root of all of that. There's t. Now let's look. So this gives you the orbital period of a satellite. By the way, if you want to go through this, I'd recommend it, but what you'll see out of this is that this period works out to be in seconds. It's not years, it's not days, it has to be in seconds. So, if you know the orbital period, the radius of a satellite, you can calculate this. You'll see later on that even in like in near-Earth orbits, in seconds, this will always work out to be something times 10 to the third. Okay? So, if you get something 10 to the 6th, you probably forgot to take the square root of it. And again, I have seen completely jacked up answers coming out of this calculation. Literally, I have got answers longer than the universe itself has existed. You have to be very careful about how you sequence this in your calculator. So, when you get done, look at it and go, wow, does this seem reasonable? Yes, Ms. Treadway?
So it is R cubed?
Yes.
Because on the big dog, it's just R. It's not R.
It is? My bad. That should be R cubed.
Our actual ones going to be changed.
The test.
No, it is R cubed.
Oh, jeez.
What?
Big dog.
Big dogs change from year to year?
No, yeah, I do. I add stuff, new stuff to it. Right now,
Just to
the
get the
estimate
really
is
tiny
about
numbers.
14.8 billion years.
Like they're cute.
Which is wrong.
Okay. What's your logic?
Huh?
Second.
Yeah, they actually got a, if you did their math backwards, it's going to be a bigger number. I think they moved the mass of the Earth and multiplied it instead of divided it, and they forgot to take the square root.
That's a big number.
Yeah.
How do you?
Okay. So here's the bigger thing. If I look at this and I increase the radius, what's going to happen to the value of t?
It's going to go up.
It's going to go up. Okay? So you're going to have a longer and longer time. So that corresponds with the idea that if you move a satellite into a higher orbit, two things are going to happen. It's going to slow down. Okay? We're not going to be going as fast. And you have a greater distance to travel because you're in a larger orbit. So you're in a larger orbit, you're going slower, that makes the period for one rotation become much less. Okay? All right. Now, what if I want to solve this equation, Kendra,
What?
for mass?
If you want to solve it for the mass of the Earth,
Yes, or whatever you're orbiting.
you would divide by gravity and
No, that's not gravity.
gravitational something
Constant? There you go.
and then also by t squared.
Okay, so this would be 4 pi squared r cubed over big G t squared, right?
Mm-hmm.
Now, do I need to do anything with that?
No.
No, that's just it. So, these are the most two common versions of this equation, what you're going to solve for. Now, make sure, and I apologize, I forgot that I left off an r cubed when I typed that up. But that, make sure, and I will change it on the equation sheet, okay? That it's r cubed, when you get for the test, it's r cubed, chill out. Okay, now, here's what's going to be vital, and we're going to work a problem with this in just a second. This t, when you put it, if you're given the value of a period of like a moon orbiting, say, Jupiter, this t probably is not going to be in seconds. Probably going to be in hours. It might even be in days. This t has to be in seconds because the only version of time that exists comes out of this big G, which is your newtons, which are kilograms meters per second squared. So this t, listen to me, has to be in seconds. Okay? Has to be in seconds. All right, so let me pull up a couple problems and we'll make sure that we can use these equations.
Do I have time to
Stop
sharpen my
that for a
pencil real
second.
fast?
Yeah. Sharpen pencil. So here's the setup.
He said take this.
Throw it out. Throw it out. Throw it out. I want you to show us how good an athlete you were in high school with that.
With that.
Two-seamer.
Throw them at you.
Bang.
All right. So here's the deal. So if you can do all of this, we'll be all right. So
I have such big.
you got a satellite 122 kilometers above the surface of the Earth. Determine the velocity and the period, the centrifugal acceleration, and g at this altitude. So there's 4 things that we need to do. And if you start wrong on this problem, everything is going to be wrong. Okay? Literally, everything is going to go wrong. So first off, what are you going to do wrong with that 100?
You're not going to square it.
You're not going to put it into meters.
You're not going to put it in meters. right? Okay? So the first thing you can't work with because it's in meters. Okay? You gotta change that. Are you gonna multiply by 1,000 or divide by 1,000? Multiply, don't divide, or otherwise you get an orbital radius of about like this. Okay? So that's going to be 122,000 meters.
Do you have to add
Now, I have to add what?
the radius, like, of the Earth?
Earth, right? There's the Earth, right? We're orbiting here. So somebody take 122,000 and add the radius of the Earth. Do not round that number, okay? Do not round it, because you've got to use that number in everything else going forward. When you do this, do not round the number. Hairball. Okay, so somebody have the radius of the Earth. Let me know what you get.
Did you show me like list off the digits or
Huh?
just list off the digits like
Yeah, tell me what you get. 6 point something.
6 point? I got okay, 6.4933.
Times 10 to the 6th
Yeah.
meters. Okay. So, once you get that number, you're going to use that from there on out. That's going to be the radius. So, if you screw this up, everything else is going to go south. Okay? Everything else is going to go south. Okay, so we got that.
I'm putting in my calculator right now, so I don't have to.
6, it's,
Hey, look,
okay,
it's on
it's
there,
on
right
your
there,
equation
right there,
sheet.
right there, right there. There you go.
Okay.
Stop.
So, let's start with the velocity. So we're going to have V equals what? The square root of
G and
big G mass over
radius.
R, right? So I've got big G and then my radius of 6.4933 times 10 to the 6th meters. So this is 10 to the negative 24th, or 10 to the negative 11th, that's 10 to the 24th, that's 10 to the 13th. I get an order of magnitude around 10 to the 7th underneath the radical, puts me something around 10 to the 3rd for an answer. So, what'd you get?
7.83.
7.83 times 10 to the 3rd.
Ballpark.
Everybody cool with that? If you punch this numbers into your calculator and you can't get this, figure out what you're doing wrong.
You said the image the mass of the Earth?
Yes. Because I've got, this is the surface of the Earth.
Is
This
that
is,
7.83?
yeah?
Alright.
Everybody cool with that? Okay. Now, period of the satellite. Period is going to equal 4 pi squared r cubed. And again, here's my radius, 6.4933 times 10 to the 6th meters divided by big G mass of the Earth. Now, here's what you're going to forget to do. This thing, I lost my 3, this radius has to get cubed, okay? That, because you're talking like an order of magnitude of like 10 to the 12th difference if you don't cube this. That's kind of a big deal.
Oh.
Now, if you want to make this a little bit simpler, okay? If you want to make this a little bit simpler, if you want to, this is purely optional. If you don't like punching in 4 pi squared, what's the square root of 4 pi squared?
4 pi?
2 pi.
There's 2 pi square root.
2 pi, right? Okay? So sometimes you'll see that period equation written as 2 pi times the square root of r cubed over big G m. So if you don't like 4 pi squared, you can just do all of this and then multiply by 2 pi. It's personal preference. You're going to get the same answer either way. The ultimate thing actually is that you take the square root of this whole thing, because that won't ever change as long as it's the Earth. And then the only thing you're left with is cubing the radius and taking the square root of it, otherwise known as Kepler's law. Anyway. So what'd you get?
A bad answer.
A bad answer.
Yeah, it was like 8 point something to the -4.
Seconds?
Yeah.
Yeah, that would be bad. I would have to make fun of you at that point.
Yeah.
More than you already do?
Yeah, that would be horrible.
Yeah.
How does 5.21 times 10 thirds?
I like 10 to the third.
I also like that answer.
So, Mr. Taylor, what did you arrive at?
5.21
5 point what?
21
Times 10 to the third
second.
seconds. 5.21 times 10 to the third second. Anybody else?
Set to the negative.
You concur. Mr. Rollins and Mr. Taylor are co-authoring
I
the
cannot
study.
get that answer.
Now, out of curiosity, Mr. Rollins, take this answer and divide it by 60. All you have to do is divide it by 60.
All right.
What you get?
87.8.
So about 88 minutes, right? So this is about 88 minutes, right? Which is about an hour and a
Is that
half.
what you're supposed to get?
So what that means is this satellite is orbiting the Earth every hour and a half. And this is about where like the space shuttle orbits, about the altitude where the International Space
I feel like
Station
I did
is.
something wrong.
This is where a lot of near-Earth satellite orbits are.
Thank you.
About an hour and a half. Okay, so which is kind of cool because they're making so many laps around the Earth as this thing goes. Okay, so are we cool here?
Hold on.
Everybody know how to get this. If you cannot get this, figure out what you're doing wrong, because you're going to have a whole bunch of problems like this that are going to involve this calculation. So if you can't get it, figure it out. Okay? We're good.
Yep.
Got it?
Yep.
Okay.
How many problems is this time?
Do you have a calculator charger?
I have my number.
Go ahead. What?
Do you have a calculator charger?
I don't.
Yeah.
Okay. Now,
Letter.
so we got the first two done. Let's just, what do we get from the velocity?
7.
7.
I did.
Point
I got it. 8.
3 times 10 to the third.
Okay, times 10 to the third meters per second. We got an orbital period of
2.
5.21
Times 10 to the third.
times 10 to the third seconds. And we said the orbital period and velocities, even the moon, the earth, typically are around 10 to the third. Okay? Typically, that's where they're at. All right, so we got these two done. Now, I want to figure out the centripetal acceleration that this satellite is undergoing. Now, why do I even know that this satellite is undergoing centripetal acceleration? It's going in a circle, okay? If it's not undergoing centripetal acceleration, this is bad, okay? Because this satellite now is drifting off into space because of inertia in a straight line. So we want this satellite to undergo centripetal acceleration. If not, bad things have happened. Okay, so there's a couple of different ways that I can get the centripetal acceleration. What's one option?
4 pi r divided by t squared.
So one option is that I could go 4 pi squared r over t squared.
Or
I'm going to use the exact same radius that I had. Now I've got the value of t. Boom, I can do that. That's one option. If you like that, go with that. What's another option?
v squared divided by r.
I could also use v squared over r. Now again, what is this centripetal acceleration not dependent upon? The mass of the satellite. It is not there. So whether this satellite is Hank the bowling ball or the International Space Station is going to be the same centripetal acceleration. Now, so which one do you want to go with? The second one, okay? So we've got that velocity of 7.83 times 10 to the third meters per second. That's going to get squared. And what was our radius?
6.4933 times
6.4933
Times 10 to the 6.
times 10 to the 6 meters. It's the exact same one that we had. So I'm guessing it's got to be less than, it's probably around 10, less than that, a little bit, ballpark.
Yeah.
Yeah, 9.44.
What'd you get?
9.44.
9.44
Yeah.
meters per second squared. Okay?
So
Right.
this thing is always accelerating at that rate. If
Yes.
Then why isn't it just going super, like, extremely fast?
Okay, this is its centripetal acceleration, not its linear acceleration. Okay? Yeah, we did have to have that to get it up to this speed. Okay? All right,
That'd be crazy.
one thing left to do, calculate G. There's only one way to do this. What can we do?
Big GM divided by
Times mass of the earth.
Big G M divided by R squared, right?
base, or I guess.
Which is going to be 6.4933 times 10 to the 6th meters squared. So do this. This is why I said that you can do this so often you multiply big G by the mass of the earth. That's why if you want to store that as a separate number, that's the most common calculation of big G times the mass of the earth. So what'd you get?
Oh, still do.
Okay, let me know.
6.14 times 10 to the...
There is no way on God's
Yeah.
green earth.
I didn't square it.
Oh my god.
See?
9 point.
Oh.
crap. 3.8. I don't know.
9.46.
9.46? Okay? So basically you'll notice that it's the exact same thing.
Whoa.
Okay? It's the exact same value. Why does it have to be the exact, it's within rounding with our radius and stuff, it's the same value. Why?
Otherwise it drifts off into space.
Huh?
Otherwise it drifts off into space. They have to be equal for it to stay in orbit.
True.
Or it's all.
Okay? So look, here's the grand idea. This satellite, okay, here's a satellite, boom, it's in orbit around the Earth, right? So here's the grand idea. The gravitational force pulling on it, right, has to equal the centripetal force. Big idea. Now, this centripetal force is generally mass times my centripetal acceleration, okay? And that's going to be the mass of the satellite. Well, that's going to equal big G times the mass of the satellite, mass of the Earth, over R squared. Okay, well that's kind of cool. All right, satellites cancels out. Those always drop out. So now I'm left with big G mass of the Earth over R squared. Well, when you take big G times the mass of the Earth over R squared, what do you get? You get what variable do you get when you take big G times the mass of the Earth over R squared? Little g, right? So little g equals your centripetal acceleration. Okay? This has to be this. So like if you put something in a near Earth orbit, like I mean right at the surface of the Earth, what do you think the centripetal acceleration is going to be? If you could put it in orbit right at the surface of the Earth, 9.8 meters per second squared. Okay? Because that's what the value of g is. So as you go higher and higher into orbit, the g is going to get smaller and smaller and smaller. So if you were to draw a graph, okay, saying here's the value of your centripetal acceleration, which is the same thing as g, versus radius. Okay? Well, first off, what's the minimum radius that you have to even think about this? Yeah, you got to start with the minimum radius of the Earth. We're not going to do well orbiting inside the Earth. Okay? So the minimum, we're going to have the radius of the Earth. And let's say that's 9.8 meters per second squared. So the radius of the Earth, that's going to be at 9.8 meters per second squared. So as you go beyond the radius of the Earth into higher and higher orbits, what's this line going to do? is going to go down in an exponential curve because of the fact that it is r squared. So could you ever technically go to 0?
No.
No. So when everybody says that they look at the International Space Station and all this, oh, they're in 0 gravity. No, they're not in 0 gravity. It's just that everything is experiencing the exact same acceleration. That's why it appears to float. Everything's just in a state of free fall. They couldn't even orbit if they were in 0 gravity. Okay? One last problem and then we're done.
What's your order of No, stop. Please stop. I'm asking a serious question.
So,
And divided.
here's the deal. So, newly discovered, even though kind of part of it, so a newly discovered planet has a moon with an orbital period of 20.5 hours and a radius of 3.68 times 10 to the 6 meters. What is the mass of the planet? So, when you look at how we figured out like the mass of Jupiter, the mass of Saturn, okay, any planet that has a moon. So any planet that has a moon, it's very easy to find the mass of that planet. Because again, you have to realize, we can't stop the planet in its path, put it on a scale and go, oh, here's the mass. So what we observed, here's this planet. Luckily it has a moon, 20.5 hours. This radius is the distance from the center of the planet out. If this was the distance above the surface, I would tell you it's 3.68 times 10 to the 6 meters above the surface of the planet. Okay? But if you're just told, hey, this is the orbital radius, that is the number. Okay? There's nothing else to do with it. That is the number. Leave it. Don't touch it. Boom. That's it. It's a gift. It's in meters. We don't have to do anything. So what equation am I going to use to start with?
The Swiss Army knife?
D equals.
No. I wouldn't do.
Is it GMT squared?
Yeah, that Swiss Army knife, right? You got. So what's that big one that involves T? GM
T squared.
T squared equals
4 squared.
4 pi squared r cubed. So I know what G is. I know what T is. I know what R is. What's the only thing I don't know? Mass of the planet. So this is going to be 4 pi squared r cubed over gt squared. So, am I just going to take the 20.5 hours and put that in there?
No.
No, bad, horrible, bad, no, bad. Okay, bad.
Okay.
You get the point. It's bad.
No, it's not good.
Not good.
Not good.
Okay,
Bad.
and especially because it's squared, and if you don't change it into seconds, you're going to be off by like a power of 10 to the 6. And people go, oh, so what? You're off by a power of 10 to the 6. Okay, you're off by 1,000,000. All right? I want you to be my banker. Hey, overdrafted by a power of 10 to the 6. Oh, that's okay. Okay. So, when you convert the 20.5 hours into seconds, do not round that number. Keep it with all the digits that you have. So I'm going to have 4 pi squared. I don't have to do anything with the radius. 3.68 times 10 to the 6 meters. G. Now, somebody take 20.5 and multiply that by 3,600. 73,000 what? 800? Exactly?
Yes.
Now, here's also what you're going to forget to do. Trust me, you're going to forget to square those seconds. Trust me, trust me, trust me.
You know what else you're going to forget to do?
What?
Cube the radius because you forgot to even put it there.
Who's teaching this class? Alright, go.
Here, I'll sit there. Trust me. Trust me.
No, I literally just figured out.
You want me to do it?
I just figured out
You
how
want me
store
to?
numbers.
Hey, do you want me to teach, bud? You just give
So what'd you get?
me your word, and I'll go up there and teach you guys a little thing or two about some biology or whatever we're in.
Play it.
Biology.
Oh, you comedian, you.
Where you said we were in
Generally,
meteorology.
anything that ends in ology isn't real science.
Why?
Allison calls
Meteorology.
meteorology fake science.
No, it's actually legit. But
Fake science.
there's so many unknowns that you can't account.
Yeah, you tell that to Bill Nye, see what he does. He'll go off on you. He taught me meteorology. He taught me the water cycle.
Okay. Anyway, what'd you get? Has no one run the
I
number?
did put
I
it
don't-
in.
My
Don't
calculator's
wanna say
dead. You have a charger?
Dude, I got something
What?
different. We all got
What'd
something.
you get?
Does anybody have an Android charger?
I know, mine needs that too.
What kind of charger? 6 times
Huh?
10
I have my
to the
calculator
6.
charger.
You do?
Alright, you want me to run the number?
What should it be
I want some run
around?
the number. All right, I'll run the number. Or throw a number out.
I don't have my calculator.
Yes,
Never
okay, I
mind.
think-
I don't have my.
Well,
Okay, Miss Treadway.
Don't.
I'm not, I won't pass judgment.
I have a
I
question.
got 5.42 times 10 to the 21st.
That's also
Okay,
what
that's what I got.
5.42 times 10 to the
See, nobody is going to say it.
That's what I got.
So,
Okay?
are you cubing just the radius or that whole top number?
No,
the
you're
radius.
just cubing just the radius, because this is 4 pi squared.
Oh shoot. Oh shoot.
No, E. Okay. All
Where
right.
the head strap wrong?
Good? Got it?
Yes.
Where the heck?
Okay. So, stop that. Let's go back and look at space and time.
Yay.
Where we're at, Newton has done his work, late 1600s, everybody got his cool, we can describe the motions of the planets. Led to a big philosophical discussion, like for example, if you know where Mars is at any given instant and you can calculate its velocity, then not only do you know where it is now, but you can predict the future positions of Mars. You can say, hey, where's Mars going to be in 5 years? Oh, okay, cool, you know where it is. Then you can also work backwards. So it's like a clock that you unwind. So then you could go, where was Mars 10 years ago? Where was it 20 years ago? And so that led into a philosophical discussion, is that Mars is just like a clock. It's following a set pattern of gears, and Mars is going to move around in this orbit. So then they said, well, then the Earth did the same thing, okay? Earth was just moving in its orbit, forwards and backwards. And they said, well, if that works with the planets, then does that work with us as well? In other words, are we just following out some initial set of conditions that was established by a clock, and we're following this path because that's what it does? So, land. Okay. So, that was cool for about 300 years. Then along comes Albert Einstein. So, we knew what gravity was, we knew how to calculate it, really didn't know how to describe it. So, what Einstein did is he viewed space and time as like spandex, basically. Okay? So, so, what I'm going to do is I'm going to take this small ball and I'm going to roll it across. Okay? Now, that pretty much follows Newton's first law of motion that says for no outside force, it's pretty much going to travel in a straight path. So I really can't make it travel in a curved path. So it's just going to go back and forth. It's going to slow down because there's some friction, and it's going to settle right there. So how Einstein viewed it, he says, okay, so let's say this is the Earth. And then we're going to put a sun in the middle of our solar system. So what that's going to do is cause a curvature of space and time. And the more stuff you put in there, the deeper that well becomes, and the more space and time gets warped. So now, if I take this same Earth and then roll it, now it doesn't go in a straight path. Now it follows a curved path. So if you can imagine this traveling in a certain velocity around this, so Einstein says the Earth orbits the sun. Yes, there's gravity, but gravity is creating this gravitational well. And so what we're doing is that we're just riding the ridge of that particular curvature of space and time. Mercury is closer, so it's closer to the bottom of that well, so it's riding a curve that's steeper, so it has to be going faster. The further out you are, the less space and time is warped, you don't see as much. Now, so Einstein took it one step further. He says, okay, not only can a gravitational pull like the sun alter the path of the Earth, it can also bend light. And so this is actually where Einstein really did his most important work, is that it was solar eclipse, and there was a star that wouldn't be visible normally because the sun is in the way. So there was going to be a solar eclipse. The sun was going to be blocked out. Because the sun was blocked out, we were able to see this star that was off to the left. So, but that starlight, as it came around the sun, was going to be bent. So it would, to us, appear that that star is over here because that light is getting bent as it came around. In reality, it's here, but the light gets bent. So when we see it, it looks like it's at this point. So Einstein said, and he predicted, okay, this is this star. This is where the star is going to appear. It's going to shift a little bit because of this gravitational field. Set up all the experiments, they did it. It matched perfectly what he did. Hay validated his theory of relativity, general relativity, and he became like a rock star. Okay, front cover of the New York Times. It was cool. Okay, so right now all of us, to a certain extent, are warping space and time because of the fact that as we go through this, and now don't freak out and go, put that on your college resume. What do? I warp space and time. Okay, everybody does. Get over it. So this is where this gets a little bit interesting. So let's say that we have two different masses. So I'll put like a 200 gram mass here, and then maybe a 100 gram mass here. Okay? So let's say that we want to go to the moon. Right? So here's the Earth. We're going to orbit the Earth a couple times. Then we're going to fire the rockets and we're going to go to the moon. Well, here's the problem with this idea, is that if I fire the rockets and I try and go to the moon, and if I don't leave fast enough, then the only thing that's going to happen is that it's going to, oh, too fast, okay? We're going to stop and we're going to fall back towards the Earth, and that's fairly embarrassing. It's like, oh, we tried to go to the moon, miscalculated the velocity, here we come back again. Okay, so, but there's a point, and it's called the Lagrange point, where the gravitational pull between the Earth and the spaceship and between the moon and the spaceship is completely equal. Okay, it's called the first Lagrange point. There's actually two of them. One is out here, one's in here. It's a mathematical construct. You guys will do this. So here's the point. If I put it right in the middle and let go of it, what happens? It goes towards the Earth, right? Not far enough away from it. So there's a point, like the ridge of this space and time. If I did it on the other side of it, though, it accelerates towards the moon. So there's one point where it balances. So at that point, it's like the ridge of this curvature of space and time. I have an equal pull towards the moon. It's like a tug of war. The moon's pulling on it, the Earth is pulling on it, and right now it's balanced. So if you could take a spaceship and park it at that point right there and just stop it right there, it would be cool, because then as the moon and the spaceship would orbit, they would stay in perfect alignment like this. Okay? They would always be continuously lined up because it's balancing this curvature and this pull between the Earth and the moon, and you're right there. So that's one of the things you're going to do today is calculate this Lagrange point, okay, named after the French mathematician that came up with it. There's actually like 6, but we're only going to do 2 because the other ones get really, really weird. Now, let's say that you want to have a binary star system. Okay? So now you have 2 gravitational wells. So now things get fairly weird. Okay? Because then you have two gravitational wells that you have to worry about. So now, since you have a double warping of space and time, and the Earth and the Moon do this as well, we actually orbit around what's called the center of mass. All objects orbit around the center of mass. Center of mass between the Earth and the Moon is actually inside the Earth, which is cool, because otherwise, like the Moon and the star, or the Moon and the Earth would be doing this around each other. Now the Moon just kind of does this. So when you have binary star systems, the math gets much more complicated because of the fact that you're always, oh, that'd be a good one. Oh, it's going to stop in the middle? Oh, almost, okay. So now you have two gravitational pulls. And where it gets complicated is that because even if I'm here, I'm not outside of this gravitational pull, okay? The dominant one is here. So the math gets really, really weird because you're always looking at a varying change of rate because you're just not worried about this one, you have to worry about this one as well. And then in the middle, you can get all sorts of weird things happening. Now, one of the things that's on the sheet is this concept of escape velocity. And this does a nice job of showing this. So if I'm here, and like if I just take this and I throw it up, right, it comes back down. If I throw it faster and faster and faster, it's going to go higher and higher and higher. Okay, so it's kind of like this. If I throw this out and go pretty slow, okay, it comes back. The faster I throw it, the farther it goes out, but it eventually comes back down. But if I throw it fast enough,
It wasn't even on the sheet that time, you just threw it.
I did. But if I throw it fast enough, then it doesn't come back. And that's what's known as escape velocity. Now, escape velocity has a similar type of deal for velocity. V equals, but now there's a 2, because it's 2 gm over r. The 2 comes from kinetic energy and potential energy. We'll drive the equation later on. So what escape velocity tells you is how fast you have to be going to leave a gravitational field. So if we want to go to the Moon, we have to be going fast enough to leave the Earth's gravitational field. If you don't, then it's just going to come back down, and that's fairly embarrassing. Okay, got it? Good? Let me get you started on problem number 10. Okay? Because number 10 is going to look horribly, horribly daunting. And you're going to flip out, but there's some shortcuts that you can take. So here's the basic setup on number 10. Here's the Earth. Here's the Moon. What I want to find is the point in between where that lunar command module has an equal pull towards the Earth and towards the Moon. Okay? That's what we call Lagrange point number 1. Lagrange point number 2 is actually out here. We'll find that one as well. But the one we're worried about is this one because that's going to determine once it crosses that point, then it's going to start to speed up. Okay. So, you know the mass of the Earth. I've given you the mass of the Moon, what's the mass of the Moon? It's on the problem. Or it's up there a little bit.
7.35 times 10^27.
That's it, 7.35.
Terry, what you're going to do is just write the paper.
Okay? And then I've given you this distance of 3.844 times 10 to the 8th meters. Okay. So, let's get started on this problem before I turn you loose. Okay? I want you, everybody starts off on this problem. So let's say that here's
What is that 10 to the what?
what?
The distance.
To the 8.
3.844 times 10 to the 8th meters. It's on your sheet. Okay? So, let's calculate the gravitational pull between the Earth and the lunar command module. Okay, so I want to calculate the pull going this way. I want to calculate that force. I'm not worried about the Moon. I'll deal with the Moon later. I just want this force. So, I need 3 things to calculate that force. What 3 things do I need beyond big G? Mass of the Earth.
And
Radius.
We'll deal with radius later. Mass of the lunar command module. And that's not these common multiple. And then I need the distance, right, between these points. But here's the problem. I don't know what this distance is. So let's just let that be x. But that's got to be x squared. Okay? This isn't x, it's x squared. Now, that has to equal the force between the Lunar Command Module and the moon. Okay? Just like a tug of war. So that's going to equal big G, mass of the moon, mass of the Lunar Command Module. But now what do I have?
A distance.
Another distance. Is it just going to be x again? No. Well, what's the total distance? 3.844 times 10 to the 8th meters, right? That's the total distance.
Minus
This distance is x. So what's left over? That distance minus x, right? So this is going to be 3.844 times 10 to the 8th minus x quantity squared. But now, as ugly as this looks, it looks pretty ugly. But since these are equal, what can I do with big G?
cancel out.
Cancel out big G. What else drops out? Mass of the Lunar Command Module. Okay? So now, as bad as it was to start with, now this is a little bit more manageable. Okay? Now, at this point, here's what I want to do. I hate fractions. It's just bad. So I want to cross multiply this thing. Okay? So I'm going to cross multiply. So I'm going to have the mass of the Earth times 3.844 times 10 to the 8th minus x quantity squared. And that's going to equal the mass of the moon times x squared. Okay? Now, again, mass of the Earth, really, really big number. Mass of the moon, really, really big number. Okay? I want to simplify this. So I want to divide both sides by the mass of the moon. Okay? So now, the beauty of this is that now I just have x squared over here. Okay? X squared. It's much more manageable at this point. So, do this. And that way everybody's got the same number. Somebody take the mass of the Earth and divide that by the mass of the moon, 7.35 times 10 to the 22nd.
Is that on the paper here somewhere?
Yes.
And divided by the mass of the moon.
Take the mass of the Earth and divide it by the mass of the moon.
The 7.3.
What'd you get?
You said the mass of the moon is 7.35 times 10 to the 22nd.
Well, yeah, that's what you guys said it was on the paper.
Yeah.
81.3.
8.
I got 4.
I got 8.1.
I got 2.
Dude, you're like, not rocket appliances, guys.
I got
If
8.1.
you say rocket appliances,
I'll give you that. I'm going to walk out of the room and I'm
Why'd
going
you
to... No.
You have to put a
22nd.
Okay.
little thing.
Here, I got it. Don't, no one say
What did it
anything.
go to?
4. Yeah, 4.3.
Goes to the 8. How is the 22nd?
It's at 47 or 45.
What, now, Ms. Trenway, what you get?
It's just like 8.13 times 10 first.
So, 81.35?
Yes.
That.
I feel uncertain.
That's what I
right
got.
now.
No, no, we're
No,
good.
that's because you're dividing a huge number by another.
Yeah.
I mean, but
So,
Okay.
81.35. Remember that number,
Yeah.
81.35. That's what you got, right?
Yeah.
Okay. So, here's what we're going to do. Now we're going to clean this up even more. So, we've got 81.35, right? Times 3.844 times 10 to the 8th minus x quantity squared is going to equal x squared. Okay? So this just made this number a lot more manageable. Now, at this point, there's two ways that you can work this problem. There's two ways that you can work this problem. One option is that you expand this binomial. Okay? You FOIL this thing. Just like, you know, if you have 4 minus x quantity squared, that becomes 16 minus 8x plus x squared. Okay? And then you distribute the 81.35, you combine all your terms, and you use the quadratic formula. You can do it that way. It's an option. It's an option.
Next,
Okay? Next.
pass.
Next. But because this is a quadratic, how many roots do I need?
A positive 2.
I need 2 roots. Okay? I need 2 roots. That's the key. So to make this simpler, we're going to take the square root of everything. Okay?
Oh, yeah.
Treadway likes that.
That's good.
Okay, so somebody take the square root of 81.35.
9.02.
9.02. Now, that's going to be plus or minus 9.02. Okay? This is going to be important. Plus or minus 9.02. Now, when I take the square root of this whole thing squared, that just becomes 3.844 times 10 to the 8th minus x. And this just becomes x. This becomes much more manageable. So this is how you're going to get your 2 answers. You're going to take, don't even worry about this negative sign.
I see where you're going.
You're going to take this positive 9.02 and you're going to distribute it over this. That's going to get you like a number minus 9.02x equals x. Get all of your x's on one side, get all your numbers on the numbers on the other, solve for x. Okay? That's how you're going to get one root. The second one, you're going to do the same thing. But now you're going to distribute a negative 9.02 over this. Combine all your x's. Divide again. So work this as 2 separate problems. Start here, distribute a positive 9.02, get a value for x. Start over again, completely separate. Start with a negative 9.02, distribute that, here you go. So if you do this right, here's the Earth, here's the Moon. You're going to get one Lagrange point that's inside the radius of the Moon's orbit, and you're going to get another one that's outside that orbit. Okay? So if you do this right, one's going to be here, one's going to be here. They're both going to be 10 to the 8th. Both of these roots on number 10 should be 10 to the 8th, if you do them right. And then don't forget to answer that question, what happens when it crosses L1? Because what happens is that you all are so excited about getting this number that you flip out and then you don't answer that. Okay?
So how can you tell which number is which one? Where's the number relative to? Is it the Earth?
You have the distance from the Earth to the Moon. One root is going to be less than the distance to the Moon. The other one's going to be bigger than the distance to the
So
Moon.
that's what I'm saying. The Lagrange point is relative
So
to
I guess
What do you... Okay, let's say this distance is 12. One's going to be 10, one's going to be 14.
I'm saying, never mind.
Thank you.
Because that's how you're going to know. Compare it to the radius of the Moon that's given in the problem.
So I'm just
This is the
divide
radius of the Moon itself. This is the
Why
orbital
am I
radius
thinking
of
this
the Moon.
through too much? So if I add this over, then
Okay.
I would get positive
All right.
x squared though, right?
So you want the
Yeah, there's
answer
probably
in terms of
No, not x squared.
It's going to be a meter.
Ratio.
It's no. It's going to be an actual distance of meters. Okay? It's going to be an actual distance of meters. Okay. Now,
Why is there a big thing?
let me explain some of these problems. Let's talk about problem number 6.
That's how many trees are going to have to kill just to kill these.
I know.
This work on science.
So let me explain what's happening on problem number 6. You have an electron with a mass of 9.11 times 10 to the negative 31st. Proton has a mass of 1.67 times 10 to the negative 27th, separated by a distance of 5.3 times 10 to the negative 11th meters and a hydrogen atom. So basically you have a proton and then you have an electron. So everybody thought, hey, atoms should just act like little solar systems where the proton is like the sun and the electrons are like the planets. Good enough. So here's what's going to happen on A. You're going to calculate the gravitational force of attraction between them. You know the mass of the electron, you're going to know the mass of the proton, you're going to know the distance between them. You're going to use F equals big G m1 m2 over r squared. Boom. Then on B, you're going to compare that to the the electrostatic force, which is 8.2 times 10 to the negative 8. So over that same distance, the electrostatic force is 8.2 times 10 to the negative 8. So you're going to compare the gravitational force, which is going to be a lot smaller, to the electrostatic force over that same distance. You're going to say, hey, it's twice as big, it's 3 times as big, whatever it is.
How are we supposed to find the electromagnetic force?
Okay.
I gave it to you in the problem. It's 8.2. I gave you the problem.
Oh.
It's in the problem. Now, when you get to C, here's what you're going to do on C. I want the same amount of gravitational force between the electron and the proton. So you're going to set the gravitational force to be that 8.2 times 10 to the negative 8. Now that's going to be your gravitational force. You're still going to have the same electron, but now you're going to figure out, okay, what does the mass of the proton have to be to generate the same gravitational force as the electrostatic force is at that same distance. So in other words, I've got to have a really big proton pulling on this tiny electron to create the same gravitational force as the electrostatic force does over that same distance. It's going to be a massive number. Okay. Now, let me give you some hints on some of these problems.
Gladly.
Always a pleasure. Let me give you a hint when you get to number 2 that those are 2 identical spheres. So they are identical. So let M1 and M2 be the same variable and you're multiplying them together. Hint, hint.
M1 and M2 same number.
No, well they're just identical.
Identical.
Okay. When you get to problem number 2, that one your answer should be something times 10 to the 3rd. When you get to number 3, that answer should be something times 10 to the 7th. So let's talk about number 3. You've got a 1 kilogram mass. I want it to weigh 3 newtons. On Earth, what does a 1 kilogram mass weigh? 9.8 newtons, because it was 1 times 9.8. So what does G have to be for a 1 kilogram mass to weigh 3 newtons? How much less? Do not make this difficult. 1 kilogram times X equals 3 newtons. What does X equal? 3 meters per second squared. So basically, in a clever way, I'm asking you, hey, how far away do you have to be from the Earth for G to drop to 3 meters per second squared? That's all I'm saying. Yeah.
Yeah,
It's obvious.
Your answers to number 8 and 9 should both be 10 to the 3rd. Your answer to number 12, where you are finding the mass of Saturn.
Oh, I'm so glad there's a back.
Yes.
Yeah.
Number 12, that answer for Saturn should be something times 10 to the 26th. 12. It's a big number. Now, when you get to number 13,
I was just looking at the question.
I don't even know what
when
that
you get
word
to number
is.
13,
Geocentric.
here's the Earth. A geosynchronous orbit means that it stays above the same point on the Earth all the time. So the only way that can happen is if it has an orbital period of 24 hours. Because if it's less or more than 24 hours, then it's either lagging behind the rotation of the Earth or it's going faster than the rotation of the Earth. So like all your GPS satellites are parked in a geosynchronous orbit because so that way they are at a fixed point above the Earth all the time.
Satellite.
So basically I'm saying, hey, how high do we have to get to have an orbital period of 24 hours? It's going to be a big number. But I'm ultimately asking for how high above the surface of the Earth. So you're going to solve for R, then how are you going to get how high above the surface of the Earth? What are you going to subtract out? The radius of the Earth. Okay? Number 16. 16 is old school acceleration equations. Okay? 16 is pure old school. That's all it is. Pure old school. When you get to 18, 19, and 20, that all involves that concept of escape velocity. The definition and everything about escape velocity is on this last page of notes. Hand equation, V equals the square root of 2gm over d. Everything that you need to know about escape velocity is back here. Okay?
At least there's no free body diagrams.
There are no free body diagrams. You speak words of truth. So, let me give you some words of advice. This is due on Monday. The test is Monday. Do not wait until Sunday night to try and do this.
So this is
Okay?
the gravity assignment that everybody makes?
Yes.
Is this the rocket problem? Because I asked a former student about it and he said it's a rocket problem.
No, that's moment of inertia.
So we have another.
That's a satellite problem.
So we have another problem to look forward to.
Oh yeah, that's a satellite problem. That's a good one.
Great.
Yeah,
I like how you just get this evil smile.
I know
you
you
just
do.
have this pleasure.
Yeah, it is. That's a good one.
This isn't even that hard.
Shut up.
Okay, so we're going to go over this tomorrow. Okay, you're going to get the review tomorrow, but the test is on Monday. So the beauty of it is you don't have that many equations to work with. Where you're going to run into trouble, in case you haven't noticed, you're going to lose an exponent. You're going to forget to square something. You're going to forget to cube something. Okay, and then you're off by like 10 to the 6th. That's bad. Yeah. So, okay, I'm done.
How do you get
This number is
G,
very
M1,
interesting.